So I just finished lecturing on the EA equals R factorization. The key takeaway there is that EA equals R means E is non-singular, and E times A is the reduced row echelon form of A. And if you happen to have that matrix E, you can make lots of problems involving A a lot simpler. And the way we calculate E is by doing the Gauss-Jordan algorithm on A, and then independently keeping track of each of those row operations and storing them in elementary matrices. And then if we multiply all of those elementary matrices in the right order, that will give us the matrix E. I don't have a ton to say here in terms of Sage calculations, except I do want to show you that Sage has a predefined syntax for defining elementary matrices. So I've written out some text here, carefully describing how to define elementary matrices. You should read this, but I think I can quickly explain what's happening here in words. So the first thing to know is that Sage is written in Python, and in Python, all counting starts at 0. When we humans do things, we typically count starting at 1. So I call the first row of my matrix row number 1. In Python and in Sage, they view the first row of your matrix as row 0. So that's the only thing that you really need to remember here. Now remember, there are 3 types of elementary row operations, and consequently, there are 3 types of elementary matrices. The first type of elementary matrix is a row swap. And if you want to define an elementary matrix, you use this syntax, elementary underscore matrix, and then the first thing you need to input is the size of the matrix. Are you working with a 4x4 or an 8x8, or in this case, a 10x10? So you need to tell Sage how big the matrix is. Then for a row swap, all you need to do is tell Sage which is row 1 and which is row 2, but you have to respect the way they index. So here, I'm trying to represent the row swap row 4 switches with row 8. Well, as far as Sage is concerned, row 4 of your matrix is row 3 of their matrix, because row 1 of their matrix is row 0. So if I want to take row 4 and tell it that'll be one of the rows to switch, you say row 1 equals 3. So you give them the index 3 instead of 4. Then if I want to switch with row 8, instead of saying row 2 is the 8th row, you call it the 7th row, because again, the first row is the 0th row from their point of view. So input the size and tell them what the indices of the 2 rows you want to switch are, but you have to subtract 1 from your index because they start at 0, humans start at 1. If we click evaluate, I have one print statement here, and it'll tell us the matrix we just input. So the one I've predefined here is a 10x10, where row 4 is swapped with row 8. And we can see here, this is almost the same thing as the 10x10 identity matrix, except row 4 is out of place and row 8 is out of place. We switched those two. What about row scaling? The syntax here is almost the same, except instead of giving it 2 rows, we need to give it 1 row index and then the scalar we use. So here, we still need to tell Sage what size we want the elementary matrix to be. Here I'm choosing size 6. And then I want to represent the elementary matrix corresponding to scaling row 5 by the number -33. So if I want to tell Sage to work with row 5, I need to tell Sage to work with their row 4, because again, they start their counting at 0. So when I write row 1 equals 4 here, what I'm really doing is I'm working with the 5th row of my matrix. And then the scalar we're using is -33. And then my print statement will just print out this matrix. If we click evaluate, what we see is this is the 6x6 identity matrix, except we have scaled the 5th row by -33. So instead of a 1 in the 5-5 position, we get a -33. Finally, the most important row operation is row addition. And for row addition, we need to tell Sage the size. We need to tell them the row we are changing. We need to tell them the row we are using to change that row. And then we need to say what scalar we're using. So here, I'm constructing a 4x4 elementary matrix. The first row, so the row that I'm going to manipulate, has index 2, which means it's really the 3rd row of our matrix. And then I'm going to use the 0th row to, so that's the row that I'm taking a multiple of and then adding it to the first row here. And the scalar I'm using is -8. So I've defined that elementary matrix. If I click evaluate, I end up with a 4x4 matrix. And this was the identity matrix, except I changed it a little bit. We took the third row and we subtracted off 8 times the first row. So this is one way to define elementary matrices. So like what you could do is like if you are using the Gauss-Jordan algorithm, you could just like define all of your elementary matrices in here and then enumerate them, and then you could multiply them together to figure out your matrix E. So that should save you a little bit of time and headache, so you don't have to do everything by hand.